from an AIME competition, I believe, of yesteryear, long ago, maybe back in 2009. But notice we have a polynomial, and it doesn't take long to surmise that the degree of this polynomial is 8. Degree equal 8. Okay, and that's very easy to see because when you expand this, you're going to get minus x to the 9th, and it's going to cancel with this x to the 9th. So it's a contrived problem in that sense. So we're to find the sum of the roots of this 8th degree polynomial. Sum of the roots, with of course it would be impossible to find them unless you did it numerically, I guess. But we know it's an 8th degree polynomial, and so we can write it. I guess this is one of the fundamental theorems of algebra. Everything up to complex numbers can be expressed as a product of linear factors. That is an 8th degree polynomial. Any polynomial. Notice we have 1, 2, 3, all the way up to 8 roots, which is guaranteed by the fundamental theorem of algebra. Now they may not be distinct. They may be distinct. It doesn't make any difference. But nonetheless, this is an 8th degree polynomial. Now when you expand this out, it's clear you'll have a monic term. X, 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 x happens 8 times. And then what happens, you'll notice if you expand this out, and it's very time consuming to do it by hand, but all of the sum of the roots minus the sum of the roots accumulate more or less as the coefficient of x raised to the 7th power. See, that would be the next highest power. So you see, what we're looking for actually presents as a coefficient to the x 7th term. Okay, so our goal is just to see if we can figure that out by hook or crook here. And so the only thing we can really try here is the binomial expansion to expand this piece out right here. Now I went ahead, for the sake of completeness, I wrote down x to the 9th minus x to the 9th. So you'll see it does cancel, and that's what I said earlier, but here it is more descriptively. Now, this part right here is just a binomial expansion, okay? The first term of the expansion would be x to the minus x to the 9th, because it's minus x raised to an odd power. Now, the next term, this 9 choose 8, this is the binomial coefficient. It's the combination 9 choose 8. Notice there's no minus sign here because it would be minus x to the 8th, okay? And 12 times 13. And then the next one will be 9 choose 7. Now notice the minus sign sticks around. I conveniently wrote it out to the front. It would be minus x raised to the 7th power, so I put the minus out front. And then what's nice about all this is I put the ellipsis because we only care about what's in front of x to the 7th after we divide through. And you'll see that what I mean by that in a minute. Now, 9 choose 8 is equal to 9. Okay, it's the same as 9 choose 1. Now this piece right here would be 9 times 8 divided by 2. Okay, which makes that 36. Okay, and so what we get right here, folks, and again, I just did this to get rid of some of the arithmetic. You can see what I've done right here. I divided through by this coefficient in order to make this monic. Okay, again, the way it's written right now, it's not really in this form. This has to be a monic polynomial in order for the sum of the roots to present. And so the rest of this is just algebra, folks. The rest of this is just algebra. This 9 actually occurred because this piece right here is what, 36? Yeah, this piece right here is 36. And when you divide through 36 divided by 9 is the 4 you see right here. You divide through by the 12/13 right here. And so we can see that the sum of the roots will be this coefficient. So I'm going to say the sum of the roots is the coefficient of the x to the 7th term. Now that's fairly easy right here because the 12/13 cancels. One of these cancel with one of these. So this is equal to 4 times 12/13. Which is equal to 48/13. So whatever those roots are, their sum is this. We don't know what the roots are. Now another thing is kind of interesting here. If you further posited that all these roots were distinct, which it sure looks like they probably are. If all of these roots are distinct, we actually know that the real part of each of the roots would be this divided by 8. So in other words, 48, so 6 over 13 is the real part of all the roots, if you know that each of the roots is distinct. I hope that makes sense. The real part. And again, we're positing that there are 8 distinct complex roots. So we know the sum is 48 over 13, and we know there's 8 of them. So 48 divided by 13 would give you the real part. Now, I don't know really. If I'm just saying this is, if they are distinct, then 6 over 13 would be the real part to each of the 8 complex solutions. Okay, so, and of course, everything cancels out because of the complex conjugate thing, right? If you have a complex root, its complex conjugate is guaranteed to also be a root, and so you have a bunch of plus minus cancellation going on. But anyway, this is the answer to the problem right here. 48 over 13. Let's come up here and write that again, 48 over 13. And I saw this problem republished in something called Euclid's Orchard. I think Evan Chen and some other math Olympians collaborated for this document called Euclid's Orchard. And he mentioned that this was one of the easier problems in that collection of problems. So you may, and this is similar, but it's the same sort of idea, you know, where it looks like an impossible problem until you realize the only thing that matters is the coefficient of the degree 7 term. Okay, thanks for viewing.